Swayam Prabha. Digital India. Educated India.
Welcome to lecture 13 of the open course on diffusion in multi-component solids. In this lecture, I will introduce Fick's law. We will also see with a simple atomic jump model how the random atomic jumps give rise to a net flux down the concentration gradient. This helps in linking the phenomenological diffusivity term to atomic jump frequency and jump length. Now that we have become familiar with the concept of interdiffusion flux, we will now look into the phenomenology of diffusion. So, as I mentioned earlier, there are two approaches with which we can study diffusion. One is the atomistic approach, because in solids the diffusion occurs by discrete atomic jumps. So, by analyzing the atomic jump frequencies, we can analyze the diffusion, or on the microscopic or macroscopic scale we can use the phenomenology. The second approach, as I said earlier, is more important practically because it helps us to predict the evolution of concentrations in a diffusion system with the help of some experimentally measurable parameters, right. And in studying this approach, Fick's law is probably the most important that we need to study. So, we will talk about Fick's law today. So, what it says is the diffusion flux of a component I is proportional to the concentration gradient. Right. So, we can write it J I equal to minus d dCi by dx, right. In this case, this constant d is the constant of proportionality, J is the diffusion flux, and dCi by dx is the So, this is the Fick's law equation as applied to unidirectional diffusion, which means the diffusion is taking place in one direction, here in the x direction, or x denotes the distance coordinate here. The unit of flux we usually use as number of moles per meter square per second, and the concentration we express as moles per meter cube. So, the concentration gradient will be moles per meter to the power 4, and so the unit of d, if we derive, it comes out to be meter square per second. Now, what does this mean? What is the physical significance of this d? We will see it later, but right now it is sufficient to know that this is a phenomenological expression which was proposed by Fick. So, this was proposed back in 1855 by Fick, and it was proposed basically for diffusion in liquids. In fact, the title of Fick's classical paper is on the diffusion in liquids. Okay. So, he studied basically the diffusion of salt in water, and he proposed this equation or this law by drawing an analogy with two other laws of transport, right. Those are Fourier's law of heat transport and Ohm's law of transport of electrical. So, if we draw the analogy, so it says that q dot is equal to minus K A dt by dx, where K here denotes the thermal conductivity. And A is the area of cross section. So, q dot here, the q dot is the rate of heat flow per unit time, right. So, if you take A this side, it becomes the heat flux, and dt by dx is the temperature gradient. So, heat flows down the temperature gradient, and that is why you have a negative sign here. Similarly, in Ohm's law, you can write J E is equal to minus sigma dV by dx. In this case, sigma is the electrical conductivity, and dV by dx is the electric potential gradient, right. So, by drawing this analogy, Fick proposed in his original notations, if we write the amount of salt So, this is in Fick's original notation, minus k q dy by dx times dt. So, here q is the cross section area, k is the constant of proportionality, and he denoted y for the concentration, and x is the distance unit, right. So, if you take q and dt this side, and if you denote k by d, so this equation takes the form which is popularly written today as Fick's law, which is this one, J equal to minus d dc by dx. Obviously, now we denote concentration more generally with C. Okay. So, this is the law that he proposed, and then Fick also carried out experiments to demonstrate the validity of this law. Again, the experiments were with the salt and water solution. What he did is he connected two large reservoirs of solutions with a cylindrical tube, right. So, on one side there was saturated solution of salt, the other side was pure water. So, basically the salt concentration was approximately 0 in this case, and so the salt diffused from bottom to the top. So, this acted as a reservoir of salt, this acted as a sink of salt. And what was the purpose of these two? So that the concentrations at the two terminals of the tube were maintained constant. This way he could develop a steady state condition for diffusion. Steady state means the concentration, as the diffusion occurs, obviously there will be a concentration gradient which will be developed, right. In non steady state, the concentration at any x position, the horizontal position, will change with time, but in steady state the concentration at any x position, that is at along the horizontal plane, will remain constant, it will not change with time, that is the steady state. So, by making sure that the concentrations at the two terminals remain constant, we can develop a steady state. Now, as we will see later, in the steady state, if D is constant, we expect the concentration gradient to be linear. Okay. So, what he did, he made 3 such setups with change in the length of the tube, remaining else was the other experimental conditions were same. So, obviously, if D is a constant or if this equation is satisfied, or he should be able to measure flux in each of the case. Now, in steady state, the flux in a given setup should be constant at any plane, right, because at any plane the matter that enters into the plane should be equal to the matter that leaves that plane. So, that there is no accumulation or depletion of the matter in that plane, right. So, the flux should be constant, and from that we can determine this constant D, or in his notations K, he could determine the constant K, and he saw that this constant K was independent of the length of the tube, right. So, his original experiments and the law proposed was for the diffusion in liquids, but it was also later on used in solids, right. The first scientist to use this law in solids was Robert Austin. You know Robert Austin? What is he famous for? Yeah. So, he is famous for his work on iron carbon phase diagram, and as you rightly said, austenite is the name given to the phase because of him, right. So, what he did, he studied diffusion of different elements in liquids, and he also conducted an experiment of diffusion of gold in solid lead. He measured the concentration at different x coordinates in his diffusion experiment, and then applied this Fick's law and measured the diffusivity of gold in lead. Okay. And after that, this law has been used for many solids in single component system, binary, or even in multi component systems, and it has been now very popularly used across all 3 phases, solid, liquid, or gases. Okay. So, we will be for this class more interested in diffusion in solids. So, this flux based upon the concentration gradient of the component is also referred to as Fickian flux. What can be other reasons for getting a flux? If there is an external driving force, you might also get a net velocity of the components, or the net velocity of a concentration plane because of the external driving force, and it will be also added to the flux term. So, in presence of driving force or in presence of external driving force, the net flux will be right flux due to Fickian term and also the flux due to velocity of the composition plane. Right. This is more commonly referred to as drift. So, the flux term will have contribution from Fickian term as well as the drift term. We can express flux as minus d dc by dx plus c times v, right, where v is referred to as the drift velocity. So, in order to understand this more clearly, let us consider a reservoir of water which is still, okay, and suppose if I introduce a plane of ink at some position in the water, what should happen? The ink should start diffusing in the water, right. As long as the water is steady or still, right, if I measure the flux at any point, the flux of ink at any point, it will be given by the Fick's law. Right. By the way, this negative sign is here, it comes from, what is the purpose of this negative sign? Because the diffusion occurs down the concentration gradient. Right. In other words, the direction of flux and the direction of concentration gradients are opposite to each other. So, in order to get a positive value of constant, we apply a negative sign. Okay. So, this will be the flux when the water is steady still. Now, suppose instead of having a steady water, suppose the water was flowing with some velocity v. Now, I introduce this plane of ink here, and if I measure the flux at any point, at any plane, what should be the net flux here? As long as the water flow is not too fast, we can have contribution from the diffusion as well as the ink diffuses, right. But this any composition plane of ink is also moving with velocity v with the water, right. So, the Fickian term plus the drift term because of the velocity of water. So, this will be minus d by dx plus c times v, where v is the velocity of water. Okay. So, this is the drift term, all right, and the drift term will come if there is an external driving force. The external driving force may be what? If you think of diffusion in solid, it may be an electric field, or it may be a magnetic field, or it may be temperature gradient, for example. So, even if there is no concentration gradient, in presence of external driving force, you will still get some flux, right. Clear? Okay. So, now let us come to the diffusion in solid. Now, we say in solids diffusion occurs by discrete atomic jumps, right. There are interatomic planes and the atom jumps from one plane onto the next plane or within the plane itself, right. So, it is a discrete atomic jump process, whereas here the phenomenology we assume a continuous concentration gradient, right. So, we will now let us see how these discrete atomic jumps give rise to the net flux down the concentration gradient, right. So, let us try to link the two. So, consider a crystalline solid in which there exists a concentration gradient, right. So, this is the concentration gradient that I am drawing. Now, since in solids again the diffusion takes place by atomic hopping. So, if we consider adjacent atomic planes perpendicular to the direction of diffusion. So, this is the direction of diffusion, right. So, the atoms are jumping from one plane to the other in plus x as well as minus x direction, right. So, if I zoom in and see the picture of any two adjacent atomic planes, let us call this plane 1, this plane 2, and suppose we are considering unit cross sectional area of the plane. So, let us say there are n1 number of atoms per unit area on plane 1 and n2 number of atoms per unit area on plane 2. And each atom is vibrating with certain frequency. So, per unit time there will be certain number of successful jumps that each atom can make, right. So, let us call it a jump frequency. So, let us suppose the jump frequency or the frequency of successful jump from plane 1 to plane 2 is gamma plus, and the number of successful jumps from plane 2 to plane 1, that is denoted by gamma minus. So, gamma plus is basically the number of times an atom from plane 1 can jump into plane 2 per unit time. So, if there are n1 number of atoms, the total number of jumps that can occur from plane 1 to plane 2 are n1 times gamma 1. Similarly, the total number of jumps that can occur from plane 2 to plane 1 per unit time are n2 times gamma minus. Okay. We can consider equal volume element around each atomic plane, and if alpha is the interplanar spacing, then what will be the volume around each element or around each plane? The volume of element around each atomic plane will be alpha times cross sectional area, but we have a unit cross sectional area. So, the volume will be alpha, right. So, if I determine the concentrations, C1 would be number of atoms per volume. So, will be N1 by alpha, and C2 would be N2 by alpha. Now, we need to measure, let us say, the flux across the central plane let us call this P. So, what will be the net flux across plane P? There are atoms jumping from left to right, that is from plane 1 to plane 2, and there are atoms jumping from plane 2 to plane 1. So, the net flux will be the difference between the two, right. So, if I call the atoms jumping from plane 1 to plane 2 per unit time per unit area as J plus and 2 to 1 as J minus, then the net flux in P will be J plus minus J minus. Right. So, J plus is from 1 to 2, J minus is from 2 to 1. And what will be J plus? The number of atoms jumping from plane 1 to plane 2 per unit time, that will be N 1 times gamma plus, and J minus will be N 2 times gamma minus. Now, if I assume the gradient in number of atoms to be continuous, then I can know the number of atoms per unit area on this plane P by knowing the gradient, because I know N 1 and N 2. So, if I take N as the number of atoms per unit area on plane P, in terms of the gradient and N 1 or N 2, we can express it as, let us try to express in terms of N 1, should be N 1 plus dN by dx times alpha by 2. Or in terms of N 2, this will be N 2 minus dN by dx alpha by 2. So, we are making a small assumption here that the gradient is linear, which should be very close to reality, because the interatomic spacing is very small, right. So, we can make this assumption. So, now in terms of N, we can express N 1 as N minus dN by dx alpha by 2, and N 2 is equal to N plus dN by dx alpha by 2. And if we substitute for N as C times alpha, then we get N 1 is equal to C alpha minus alpha square by 2 dC by dx, and N 2 is equal to C alpha plus alpha square by 2 dC by dx. So, if I substitute in J at plane P, I get C alpha minus alpha square by 2 dC by dx times gamma plus and C alpha plus alpha square by 2 times dC by dx times gamma minus, and if we rearrange, you can take dC by dx term on one side. So, we get minus alpha square into gamma plus gamma minus by 2 dC by dx plus C alpha into gamma plus minus gamma minus. So, what do we get? In absence of any external driving force, the jump frequency in plus x direction or minus x direction should be same, right. So, we have gamma plus equal to gamma minus. So, this term will vanish. So, we get Jp equal to, let us call it gamma minus alpha square gamma, let us call it gamma s. Gamma will be the overall jump frequency, later on we will use it. So, let us call it gamma s now, dc by dx. So, we get a familiar expression which is similar to the Fick's law expression, right, minus d dc by dx. If we use d is equal to alpha square gamma s. Now, gamma s is the frequency of jumps in this particular direction, plus x direction. If there is no external driving force, then all jumps should be equiprobable, right. And how many sides an atom can jump if we consider only nearest neighbor jumps? In any crystal lattice, how many sides are available for an atom to jump? Coordination number z, right. So, we have gamma s should be equal to gamma by z, where gamma is the successful jump frequency of an atom in any direction. So, in this case, if we consider simple cubic case, in a simple cubic lattice, what is the coordination number of simple cubic lattice? 6, right. So, if we consider this atom, it can jump either onto this side or this side, or there will be 3 more, one atom in plus x direction in this cube, one atom plus z direction, and an atom in plus y direction, if we consider this as x, y, z. Right. So, there are 6 possible jumps. So, if we consider plus x direction, if the diffusion is along plus x direction, then these 4 jumps are basically not giving any contribution, right, because they are within the plane itself, they are not giving any contribution in the plus x direction. We are considering a unidirectional diffusion. So, the only jumps that matter are plus x and minus x. So, for simple cubic, this treatment that we applied will be valid, and in that case it will be gamma by 6. So, d is equal to 1/6 gamma alpha square. Okay. Now, let us look at this second term here. Whenever there is an external driving force present, then the jump frequency in plus x direction will not be same as that in minus x direction, right, depending upon the gradient of the external field. That means, this term will not vanish, it will have some non-zero value. Obviously, if gamma plus is not same as gamma minus, this term will have a non-zero value, and this is nothing but the drift term, right. So, if gamma plus is not equal to gamma minus, we get a net drift which is equal to C alpha times gamma plus minus gamma minus, and we know the drift is equal to C times V. So, the drift velocity comes out to be alpha times gamma plus minus gamma minus. Okay. So, this is how the discrete atomic jumps will give rise to the net diffusion flux down the concentration gradient. Right. So, we have linked the atomistic random jump model to the phenomenological equation of Fick's law. Now, if the jump frequencies are not same, obviously there will be a net velocity or net average velocity of the atoms of I in one particular direction, depending upon the sign of this term gamma plus minus gamma minus, and that will give rise to this drift. So, there will be contribution from Fickian term as well as the drift term. Now, we looked at the simple cubic structure. What about if I have BCC or FCC? Let us still consider cubic structure. Obviously, non-cubic structure will be even more complicated, but let us consider either FCC or BCC. Now, if we have FCC or BCC, if we consider the contribution in plus x direction, there will be also jumps at different angles which will contribute to the diffusion in plus x direction, right. So, for example, if I consider a BCC lattice, and if this is the body center atom and if this is my x direction, then if this atom jumps onto one of the corner atoms, right, this will jump in one of the 8 corner atoms, right. These are the nearest neighbors. Now, any of this jump is not exactly in x direction, but it will have some contribution in the x direction. How much will be that? Right. So, if the jump length is alpha, the contribution it will be alpha cos theta I. Theta I is the angle that the jump I makes with the x direction, the direction of diffusion. Okay. So, now we need to modify this a little bit. So, instead of alpha, the interatomic spacing for the jump I would be alpha cos theta I. So, we need to replace these things. So, instead of alpha, I will have to use alpha cos theta I. So, if I use Ni, N1 will be C alpha cos theta I minus alpha square becomes alpha square cos square theta I by 2 dc by dx, and N2 would be C alpha cos theta I plus alpha square cos square theta I by 2 dc by dx, and Jp becomes C alpha cos theta I minus alpha square cos square theta I dc by dx gamma plus minus alpha cos theta I plus alpha square cos square theta I by 2 dc by dx into gamma minus. So, if we rearrange the terms, you get minus alpha square by 2 square theta I gamma plus gamma minus dc by dx plus c alpha cos theta I gamma plus minus gamma minus. Now, let us assume that there is no external driving force. So, this term will vanish and gamma plus gamma minus is equal to 2 gamma s. So, let us denote this Jp more specifically with Jpi, because we are considering only the jump I, jump vector I. There will be how many such jumps? Z number of jumps possible, right, because the coordination number is z. So, to get the total flux, we need to sum over the jumps I minus alpha square. Now, this will be 2 gamma, but then only half of the jumps will be in plus x direction, the remaining half will be minus x direction. So, we need to divide by half, and that gamma s becomes gamma by z, alpha square gamma by z sigma cos square theta I equal to 1 to z dc by dx. We need to evaluate this summation cos square theta I over all possible jumps 1 to z, and you will find out, if you do that for BCC or even FCC, this will be z by 3 for any cubic lattice. This we will solve as an exercise in the next lecture, showing that sigma cos square theta I is equal to z by 3. So, if we substitute back there, gamma by z times z by 3, you get minus 1/6 alpha square gamma dc by dx. So, for any cubic lattice, we can express d as 1/6 alpha square gamma, where alpha is the jump length and gamma is the frequency of successful jumps of an atom in any direction. Okay. So, we saw the phenomenology based upon Fick's law, and it is also consistent with the atomistic picture based upon the jump frequency model. Clear? So, we will solve this as an exercise in the next lecture, sigma cos square theta equal to z by 3. Any question? Okay, thank you.